All right, hello class. Due to the amount of confusion there was toward the end of class regarding torque and energy inside of the magnetic moment, I just wanted to take a moment or two to reiterate some of the points that we were a little bit confused about or struggling with, and trying to make sure that everyone has the highest degree of clarity on these things before we proceed to the next topics in magnetism. So the first thing I wanted to address was the question regarding torque. Now, we did come to an answer as to why torque is represented in two different ways, but let me go ahead and clarify those 2 points. For a lot of you, you may have encountered torque with an equation of the form tau equals R cross F, where R is the lever arm and F is the force applied at that lever arm. Now, an important thing to note about this form of the equation, it takes the pivot as origin, meaning that we are tracing from our origin what is our lever arm and then crossing our force as a result. So we're taking the point around which all points turn as our center. Now that is in contrast to this form of the equation here, which I typically use and how I was taught, which takes the force as origin. Now, what exactly does that look like? It's a matter of how you choose to set up your coordinate system. So I'll take this one as our first sort of demonstration. According to this version of torque, the origin here is where we're centering all things, which means our lever arm goes out to our point where force is applied, and this would be R, and our force points upward, as expected. So when we take the cross product of this, we would say that this has a direction of negative x, this has direction of positive y, therefore the end result of the torque would be in negative z. And so that all accords and makes sense. Now, in this version here, where force is our origin, we're taking this as sort of the 0 point, and thus we have for our force positive y, and for our lever arm, we're looking at positive x. Now, one important thing to remember about cross products is that they are not commutative. So to say A cross B is not the same thing as B cross A. And so that's why we see that both of these cross products result in the exact same torque. It's because we actually end up changing the sign in the lever arm in the second scheme. So hopefully that helps clarify our initial confusion about what was going on. Now, either way you decide to set up your torque, either way is fine. You just have to make sure that you are consistent with your system. Now, one advantage that the first system here has over the second is that you just have one point acting as origin for all possible torques. So in that sense, it is a little bit more elegant and simple. In the case of force acting as the origin, you have multiple origins for each force that is contributing to a torque. So what that would mean is that when considering force 4 here, we would have to then reconfigure things to treat this point as our origin, identify this as having negative y, this is having negative x, and then cross product going through and giving us negative z as a result. So in that sense, when we get to looking at our current loops by means of the area vector, which we have over here, a lot of those questions regarding how you formulate torque become simplified because you have only one way in which you can define the area vector. And so, again, what is that rule? That rule is based on a right-hand rule where your fingers curl in the direction of the current. So we can see that the curl of his hand is matching the curl of the current through the loop. And so in that regard, things are, sorry about that, things are simplified because we only have one way of expressing that area vector. And again, that area vector has the following definition. It is area for its magnitude and a normal vector for determining the direction, again, designated by this right-hand rule. So what this represents then is another way of expressing torque for a single loop. Whereas this version here can be any number of loops. And the idea is that you can just stack loops on top of each other in a nice big coil. And as a result of stacking all of those loops, you can add this multiplicative factor to how much torque you're producing. And we'll talk a little bit about that when we come back on Thursday, what happens, and we'll handle this particular question and address what all that means. Now, I just want to also cover some of the ideas that we talked about right towards the very end one more time, just to try to drive them home. When it comes to magnetic dipole moment, this is an alternative notation to try and bundle all of the current terms together into one identity. And so we have this notation of the magnetic dipole moment, which can be designated for a single loop or for a multi-loop coil, where n is literally just the number of loops. And utilizing this, we can also write a more trimmed down version of torque, where mu here can substitute for this or this, depending on whether you're looking at a single loop or multi-loop system. Now, the idea, again, with torque is that the angle between them is dependent as drawn from your area vector down to your magnetic field vector. So in the current scheme, as I have it drawn, from the area vector to the magnetic field vector, we're going clockwise. And if we're going clockwise, then that means we're producing a negative angle, which leads to a negative torque, which means that we're expecting this system to spin clockwise from our perspective. Now, if the area vector was underneath, we would expect it to go the other way. Now, I just want to comment a little bit more on this lowest energy when the fields align comment, because I gave you the brief explanation right at the very end, but it was right at the very end. So it's very possible that a couple of the finer points I did not communicate clearly. So let me go ahead and try to reiterate. We get the difference in energy by comparing states. And we identify that the lowest energy state is with alignment, and the highest energy state is with anti-alignment, where your magnetic field and your magnetic moment are pointing in two opposite directions. Let me go ahead and clarify that comment one more time. So let's say you have your current loop, and it has its area vector pointing this way. And we have our magnetic field that is aligned with our area like so. Presently, no torque. After all, cross of the area vector with the magnetic field vector would equal 0. Though the question then is, what happens when we decide to displace the area vector slightly from its original orientation? What is the direction of torque going to be? Well, if we take a look at those vectors, and at least the components that matter, we have a slight upward, or in another case, a slight downward area vector that is pointing, and the magnetic field vector in both cases is pointing to the right. Now, if we have a slight displacement upward, based on our cross product, our torque is going to produce spin back towards that initial equilibrium position. So our torque is going to do this number if it is slightly above, or it's going to do this number if it's slightly below. In both ways, the spin is going to push it towards that equilibrium position, indicating that the alignment of A and B leads to the lowest energy configuration. Conversely, if we take the area vector, whoops, oh, I'm reaching the end of my pad. So if we take the area vector, I'm going to move over to this side just for the space. If we take the area vector and set it up pointing this way, but we have our magnetic field vector pointing in the opposite direction, like so. So this is B, and this is A. What happens now if we displace it slightly from equilibrium? So up or down, what happens? Now at equilibrium, no torque because we're perfectly anti-parallel. But once we displace from that equilibrium position, we see we either have a little bit of down or a little bit of up, but our magnetic field hasn't changed at all in terms of its direction. But the results for our torque in both cases when displaced is exactly the same. It's going to want to turn clockwise if you're going up, or counterclockwise if you're going down. But what does that impact? If we're going down, that means we're going to spin back towards alignment. Or if we're pointing up, we're going to spin back towards alignment. Now again, what happens when we spin? What happens when we spin is we release potential energy and generate, and that converts into kinetic energy. So from this point of perfect alignment, we have U max. Now the way that we can express that is through the dot product of our magnetic moment and our magnetic field. Now that means that our lowest energy state has a negative value, but that negative value is there as a reference point. It isn't truly that there is negative energy there, but it is our reference point based on mathematics which can express the kind of energy that is present in our system. So again, what does this look like in terms of the total energy released in one half spin? Well, how it would look is as follows. So if we're at, let's say, we go from here, which is 180, to 0, that means we're going from a U position equal to negative mu B cos of 180 to a U state of negative mu B cos of 0. So that would be equal to, in the one case, mu times B, and then in the other case, negative mu times B. So to go from 180 to 0, we have a change in U equal to negative 2 mu times B, where mu is equal to negative 2 NIA times the magnetic field, which then is equal to the negative change in kinetic energy, which for a loop would be equal to 1/2 I omega squared. So that is the connection between all of these things. And I hope this particular explanation, being a little bit less rushed and being a little bit more controlled, helps you understand what we were trying to discuss toward the end of lecture on Tuesday. And with that, I don't think I have anything else to add, and I hope this has been clarifying as we have gone through it. Now, there's a little bit more that we'll talk about in torque before we move on to chapter 29, but we'll cover that on Thursday. Alrighty. Thank you for watching.